Imagine an object so dark and insatiable that it can swallow stars whole and erase their existence from the universe. Picture a void with gravity so powerful that nothing, not even light itself, can escape once it is caught. This is not science fiction. It is the reality of one of the most mysterious and extreme entities in the cosmos, a black hole. Among all the planets, stars, and galaxies out there, few things rival the sheer mystery and raw power of these cosmic abysses. They are like silent predators, invisible yet overwhelmingly strong, lurking in the dark. With a single gulp, this gravitational sink can consume worlds or even entire suns, leaving nothing but a ghostly emptiness behind. The thought is almost apocalyptic, the idea of an all-devouring darkness, yet it fascinates us as much as it terrifies us. What secrets lie beyond that point of no return, deep past the edge where escape becomes impossible? What would we find if we dared to venture into that ultimate darkness? In this journey, we will explore these questions, taking a mind-bending voyage toward the heart of the abyss, an enigmatic trip to the edge of physics as we know it, and perhaps to the end of time itself. These objects are true cosmic monsters. They defy our intuitions about how the universe works. To understand how one might hide an apocalyptic secret inside, let's first grasp what it actually is. A black hole is not a hole in the traditional sense. It is not empty space, but rather an enormous amount of matter crammed into an extremely small region. Think of a star, one much more massive than our sun, reaching the end of its life. As it uses up its nuclear fuel, it can no longer hold itself up against its own gravity. The core collapses inward, squeezing tighter and tighter. If the star is massive enough, nothing can halt the collapse. The core implodes, and in a cataclysmic event, the outer layers might explode outward in a supernova, but the center keeps crunching inward. Eventually, all that mass gets compressed into an unimaginably dense state. The result is a black hole, an object so compact and with gravity so intense that the space around it is warped in extreme ways. The defining feature is the event horizon. This is the boundary, the invisible point of no return. If anything, whether it is a spaceship, a planet, or a beam of light, crosses that boundary, there is no coming back. The horizon is not a physical surface. It is more like an invisible shell that marks the region where gravity's pull becomes irresistible. To escape once you are inside, an object would need to travel faster than the speed of light, and according to the laws of physics as we understand them, nothing can do that. So anything that passes beyond this threshold is effectively cut off from the rest of the universe. It vanishes from our view, as though the abyss has swallowed it whole. How strong is that gravity? Let's put it this way. On Earth, you have felt the tug of gravity when you jump and come back down. On a neutron star, the collapsed core of a smaller star, which is an insanely dense object but not quite the same thing, gravity is already so strong that a spoonful of its material would weigh as much as a mountain on Earth. Now take an object even denser, millions of times denser, and you have a black hole. Near this kind of collapse, gravity is so extreme that if you got very close, the difference in pull between your head and your feet could rip you apart. This gruesome effect has a scientific and rather cartoonish name: spaghettification. Essentially, an object, or an unfortunate astronaut, would be stretched out lengthwise like a piece of spaghetti as it falls in, because gravity is dramatically stronger at the feet, closer to the centre, than at the head. In a small one, this stretching becomes deadly well before you ever reach the horizon. The tidal forces, the difference in gravity from one part of your body to another, would tear atoms apart. However, if you are dealing with a supermassive one, the kind that sits in the centres of galaxies, with millions or billions of times the mass of the Sun, then the scale of everything is larger. The horizon of a supermassive monster might be enormous, perhaps as large as our entire solar system. In that case, you could actually cross the boundary without immediately being ripped apart, because the change in gravity over the size of a human body at that edge would be relatively small. You might drift right past that invisible threshold without even noticing a jolt. Don't be too relieved though. Crossing the horizon only guarantees one thing: you are not coming out again. Surviving the entry does not mean surviving the journey. Once inside, as you move closer to the core of the object, eventually the tidal forces will rise to lethal levels. Deep within a supermassive one, hours or days after crossing, depending on its size, even the strongest materials known would be pulled apart. No physical object can withstand the full descent toward that central crush. For a smaller one, this disintegration happens much sooner, possibly in a fraction of a second. The end result is the same. Whatever falls in gets inexorably drawn toward the centre. Now, what exactly is that centre we keep talking about? According to Einstein's general theory of relativity, our best theory of gravity, the core features something extraordinary, a singularity. The singularity is, in the simplest terms, the final pit of gravity, a place where the mass has been crushed to a point of infinite density. Space and time, as we know them, effectively come to an end at that point. All the matter that ever fell in, all the shattered remains of stars, planets, astronauts, and anything else, reach this central point and are compressed into an infinitely small volume. At least that is what the classical equations suggest. In a mathematical sense, the singularity is where our models break down, gravity becomes infinite, and the curvature of space-time becomes infinite. It is a bit like dividing by zero in an equation. It is not something physics can handle. This is a huge problem, because infinities do not make sense in the physical world. They are a sign that our theories are pushing into territory where they no longer work. So, if we take general relativity at face value, inside a black hole is this singularity, a place of infinite density and zero volume, where anything that reaches it is basically destroyed and squeezed out of normal existence. But is that really the end of the story? What is truly inside? This is one of the biggest mysteries in physics, and the honest answer is, we do not know for sure. The interior is like an ultimate sealed vault. No information from within can get out to tell us what is happening there. We are left with our theories, our mathematical models, and a lot of tantalizing but indirect clues. Let's imagine for a moment that we could follow an intrepid explorer or probe falling inward, just to make the scenario more vivid. Suppose a brave, though perhaps crazy, astronaut named Alice decides to jump in to see what is inside. Alice picks a supermassive one for this experiment, one of those behemoths at the centre of a galaxy, so that she can at least survive the entry. She leaves her spaceship far outside the danger zone and takes a small capsule toward the event horizon. As Alice approaches, she notices some strange things. From her perspective, everything in her ship feels normal. At first, gravity is increasing, but if the object is huge, she might not feel anything dramatic right away. However, as she looks out the window, the view is bizarre. Light from the outside universe is getting distorted. Gravity bends that light around the object, acting like a lens. The stars behind it might appear as a ring of smeared light due to this gravitational lensing. As Alice gets closer to the event horizon, time itself seems to behave differently. If she looks back at her spaceship, or any external reference, she would see clocks outside ticking faster and faster. To any observers outside, Alice's time appears to be slowing down. In fact, if someone watches her fall in, they would see her approach the event horizon more and more slowly, fading and reddening, as the light from her gets stretched to longer wavelengths. As she nears the border, to the outside world, it's as if Alice never quite crosses the horizon. She just asymptotically approaches it and gradually disappears from view as the light from her gets weaker. But from Alice's own point of view, nothing so dramatic happens at the horizon itself. She just keeps falling and crosses this invisible boundary without fanfare. This is the weirdness of relativity. Different viewpoints, frames of reference, have very different observations of the same event when extreme gravity is involved. Once Alice is inside the event horizon, she's cut off from communicating with the outside. She can scream or shine a flashlight, but no signal can escape to tell her friends what she's experiencing. Inside, space and time begin to do a sort of flip-flop. In a sense, the direction toward the singularity becomes like the forward direction in time for her. Just as none of us can avoid moving into the future 1 second per second, nothing inside the horizon can avoid moving closer to the centre. It's not just that Alice doesn't turn around or chooses not to escape. She cannot escape, in the same way you cannot resist moving forward in time. The pull inward is as inevitable as tomorrow. As Alice plunges deeper, she might discover that the interior is far from empty or silent. Contrary to what you might expect, it is not a quiet, dark void. All the matter and energy that ever fell in may be whirling around or packed near the central region. She might actually see light that tumbled in behind her from the outside universe, or radiation released by other infalling material. As you approach the central singularity, or whatever ultimately replaces it, the energy densities could become so enormous that the surroundings glow with an eerie intensity. But it is a glow she will never report back to anyone, because it is trapped with her. In a sense, the inner realm could resemble a hot, chaotic furnace made of lost light and heat that cannot escape. Some theorists have pointed out that, while these objects look pitch black from the outside, the hidden interior might be wildly different, like a seething maelstrom of energy. For Alice, though, none of this is comforting. No matter what spectacular sights she might witness, swirling radiance from shredded stars, space bending like a funhouse mirror, she is on a one-way trip toward an unavoidable end point. Now let's not forget poor Alice. What happens as she gets closer to the centre? For a while, inside a supermassive one, she might actually float freely, stunned by the strange environment. But as she drifts nearer to that central gravity pit, the tidal forces begin to ramp up dramatically. Eventually, even in a colossal object, there comes a point where no material, and certainly no human, can survive the gradient in gravity. Alice would be stretched and squeezed, and the familiar forces that hold atoms and molecules together would be overwhelmed by the differences in pull from one end of her body to the other. In her final moments, she is torn apart into a stream of particles, and those fragments may be smashed into even more fundamental pieces. Ultimately, everything that was once Alice gets added to the mass of the collapsed object, contributing in some infinitesimal way to its gravitational grip. According to the classical description, all that remains of Alice, and anything else that falls in, is a contribution to mass, rotation, and charge. Physicists often say these objects have no hair, meaning that from the outside you cannot read any detailed story about what was consumed. Only a few broad properties like mass, spin, and electrical charge remain visible to the universe. Whether Alice was an astronaut, a pile of metal, or a storm of photons, it does not matter. None of those details are distinguishable from afar. It is as if the abyss erases the identity of everything it swallows, giving the outside world no clues beyond the extra gravity it adds. This idea is deeply unsettling, and it leads us straight into one of the most puzzling questions in modern physics, the information paradox. But before we dive into that, let's consider what modern physics might say about the true nature of that central point. We know that the prediction of a singularity comes from Einstein's theory of gravity alone, with quantum effects ignored. The singularity is where density shoots to infinity and the math breaks down. But physicists do not actually believe infinite density literally exists. Instead, it is widely seen as a sign that we need a better theory, one that unites general relativity, our theory of gravity, and the geometry of space-time, with quantum mechanics, our theory of the very small and the behaviour of particles. That unified framework is often called quantum gravity, and it remains one of the biggest unfinished projects in science. We do not yet have a complete quantum gravity theory, but we do have candidates and compelling ideas. Whatever the correct theory turns out to be, it should describe what really happens when matter is crushed to extreme densities, like what occurs beyond the event horizon. In other words, the true answer to what's inside demands quantum gravity. Over the years, many fascinating hypotheses have emerged about the true inner structure. These ideas are attempts to resolve the paradoxes and breakdowns that come from the classical view. One leading approach comes from string theory, a candidate for quantum gravity. In string theory, particles are not tiny points, but tiny vibrating strings of energy. That framework has inspired something called the fuzzball hypothesis. In this model, there is no traditional interior with an empty region leading down to a singular point. Instead, the entire object is like a giant tangle, a ball of strings, a fuzzball, extending out to the size we would normally associate with the event horizon. In this picture, there is no clean separation between an outer region and an inner void. The surface of the fuzzball effectively coincides with where the horizon would be. The collapsed remnant becomes more like a massive, exotic star made of stringy energy, with no singularity at the centre. Anything falling in becomes part of that stringy structure. The information about what fell in is not lost in a mysterious mathematical breakdown. It is somehow encoded in the configuration of those strings. It is a radical shift in perspective. Rather than an empty abyss with all the mass hidden at a single point, the fuzzball idea imagines a filled-in object, an ultra-dense state of stuff, with stuff meaning fundamental strings in higher dimensional space. If true, it could resolve infinities and information loss, but it remains speculative. Right now, fuzzballs are theoretical constructs without direct evidence, though they show how seriously physicists are trying to rethink the interior in a way that respects quantum principles. Another compelling idea comes from a different approach to quantum gravity called loop quantum gravity. This framework does not rely on strings. Instead, it attempts to quantize space-time itself. Within this approach, researchers have suggested that something called a Planck star might form inside. Imagine the collapsing core becoming denser and denser until it reaches an extreme threshold, the Planck density, where quantum gravitational effects become dominant. At that point, further collapse could be prevented by a kind of quantum pressure, almost like a spring that pushes back when compression becomes too extreme. Instead of forming a true singularity, the collapse would stall at a tiny size, perhaps only slightly bigger than the Planck length, the smallest meaningful length scale in physics, about 1.6 times 10 to the negative 35th meters. For a stellar remnant, some estimates suggest the core might compress down to around 10 to the minus 11 or 10 to the minus 12 meters. Unbelievably small, far smaller than an atom, but still not zero. This tiny core is what gets called a Planck star, an extremely compressed exotic object hidden behind the horizon, like the ultimate dense nugget, preventing an actual infinite density. Now here is the mind-bending part. Once the collapse halts, you might expect a rebound, like a spring releasing. In principle, that Planck star could start expanding or exploding outward. It sounds like it should destroy the object from within. But due to the bizarre time distortion predicted by relativity, time can flow so slowly in that intense gravity that from the outside, we would not see that rebound for a very, very long time. How long? Potentially on the scale of the age of the universe, or far longer. Some calculations suggest it could take billions, or even trillions of years for the rebound to become visible. To external observers, the object would appear to live out a vast lifespan, perhaps slowly losing mass through Hawking radiation, and only near the very end might it produce a sudden final burst as it transforms into a so-called white hole, releasing what was trapped inside in one last blast. In loop quantum gravity, black holes and white holes could be two stages of a life cycle. The collapsed object might, after countless eons, turn into a white hole, a hypothetical time-reversed counterpart that spits matter outward. In that scenario, what lies within is a tiny dense core, a Planck star holding the matter and information that fell in, waiting to release it in the far future when the object finally dies. This too is speculative, but it is appealing because it offers a possible escape from the singularity and information loss problem, grounded in a candidate theory of quantum gravity. There are even more exotic notions. Some scientists have wondered, sometimes playfully, if falling inward might lead out somewhere else. This idea comes from certain mathematical solutions to Einstein's equations, which in idealized cases suggest that such an object could be connected to another region of spacetime. For example, the solution for a rotating one known as a Kerr black hole, contains internal regions that, on paper, look like they could connect to another universe, or a distant part of ours through a wormhole-like pathway. In that pristine mathematical world, one could imagine avoiding the singularity by slipping through the wormhole and emerging from a hypothetical white hole elsewhere. It is a staple of science fiction to treat these cosmic abysses as portals or gateways. However, the consensus among physicists is that reality almost certainly does not cooperate. These wormhole solutions appear violently unstable. Even tiny perturbations, like a single particle falling in, would likely destroy the shortcut and prevent any safe passage. Nature, as far as we can tell, does not hand out easy escape hatches. Still, the idea remains tantalizing. Could the hidden interior be not an end, but a bridge? Some have even speculated that our own Big Bang might resemble the emergence of a white hole, possibly connected to a black hole in another universe. For now, this sits in the realm of speculation and philosophical musing, rather than testable science. But it shows how profound the question really is. It forces us to confront the limits of space and time. Earlier we touched on something called the information paradox. Let's explore that, because it is directly tied to what might be happening beyond the horizon. In the 1970s, Stephen Hawking made a startling discovery. These objects are not completely black. They can emit a very faint glow of particles and radiation, now called Hawking radiation. This happens because of quantum effects near the horizon. Particle and antiparticle pairs can pop out of the vacuum, and one falls inward while the other escapes, stealing a tiny bit of energy. Over vast stretches of time, the object can lose mass this way and eventually evaporate entirely. It was a brilliant insight, but it led to a troubling conundrum. If evaporation occurs, what happens to all the stuff that fell in? In classical physics, it was gone forever, perhaps sitting at the singularity. But quantum physics insists that information, the detailed description of physical states, cannot be destroyed, not even by gravity's most extreme traps. Hawking's original calculation suggested that the outgoing radiation was completely random, carrying no usable imprint of what fell in. If that were true, once the object vanishes, the information about everything it devoured would be irretrievably lost from the universe. Hawking initially argued that this loss might be real, even though it clashes with quantum principles, because he suspected gravity might play by different rules. Many other physicists refused to accept that, sparking a decades-long debate. This is the famous information paradox. The paradox boils down to a simple question. Does this cosmic sink permanently erase information, or is there some subtle mechanism that preserves it? This is not just academic. Its resolution might reveal how quantum mechanics and gravity fit together. Many ideas have been proposed. One possibility is that Hawking radiation is not truly random after all. Perhaps in a way that is incredibly complex, it carries information outward as evaporation proceeds, just extremely scrambled. If so, nothing is lost in principle. It would be like burning an encyclopedia and ending up with smoke and ash. The information is still encoded in the microscopic details, but reconstructing it would be practically impossible. Another proposal echoes the fuzzball idea. If the object is really a stringy fuzzball, there may be no paradox, because information is always in the structure and in the radiation it emits. Yet another notorious idea is the firewall hypothesis. This suggests that the calm, uneventful crossing we expect at the horizon might be wrong. Instead, perhaps a searing barrier of high-energy particles forms there, one that would incinerate anything trying to pass through. In that picture, information might be rerouted into outgoing radiation rather than slipping quietly inside. Firewalls are controversial because they seem to violate a central principle of general relativity, the equivalence principle, which says that a freely falling observer should not encounter anything special at the horizon. Many physicists prefer solutions that preserve that principle, meaning no drama at the boundary for someone falling in, while still keeping information safe. The debate is ongoing, but some of the most promising routes involve the holographic principle. The holographic principle is a genuinely mind-bending concept that grew out of thinking about horizons and information. It suggests that everything that happens inside a volume of space can be described by information on the boundary of that space, much like a hologram on a two-dimensional surface can encode a three-dimensional image. In this context, it implies that the information about whatever has fallen in might be encoded on the horizon itself in an incredibly scrambled form. The interior might then be understood as a kind of emergent reality built from patterns on that boundary. In this view, there is a deep connection between what happens on the edge and what happens in the bulk, the region we think of as inside. Some researchers connect this to a provocative idea often written as ER equals EPR, a shorthand suggesting that quantum entanglement might be related to tiny wormhole-like links. If that were true, then particles in Hawking radiation could remain subtly connected to the interior through microscopic bridges, allowing information to leak out without violating quantum rules. These ideas are highly theoretical, but they show how far physicists have gone to solve the paradox. All this ingenuity circles back to the central question: what is really inside? We now have multiple candidates on the table. A singularity, if we trust classical relativity all the way down. A new structure like a fuzzball or a Planck star, if quantum gravity intervenes. Or a pathway to something exotic like another universe, though that seems less likely in realistic conditions. The frustrating part is that we have no direct way to peek behind the curtain of the horizon. These objects guard their secrets jealously. We have confirmed their existence through ingenious methods, by watching stars orbit invisible masses, detecting X-rays from gas shredded as it spirals inward, and capturing the silhouette of a horizon against glowing plasma, as the Event Horizon Telescope did with M87 and later with Sagittarius A at the centre of our Milky Way. We have even heard space-time itself ring when two of these objects merge through gravitational waves detected by LIGO and Virgo, proving beyond doubt that they are real and as exotic as predicted. But none of these observations can tell us what happens deep within. They reveal the effects on the surroundings or the geometry just outside the horizon, not the hidden inner workings. So could we ever know what's inside a black hole? Directly, perhaps not. No probe we send could ever come back out to report its findings. That leaves us in a Sherlock Holmes-style conundrum, deducing the unseen from the seen. We study how black holes form and behave in hopes of catching indirect glimpses of their inner nature. For instance, if Planck stars are real, very old small black holes might give off peculiar bursts of energy as they transition to white holes. Perhaps one day we'll detect something like that. If fuzzballs are correct, maybe subtle differences in gravitational wave signals or other observable phenomena could tip us off. Some researchers have suggested that the way a black hole rings down after a merger might differ if there's no horizon or if it's something like a fuzzball. We're pushing our technology and our understanding of physics to try and get these answers. In grappling with the question of a black hole's interior, we are effectively pushing at the boundaries of human knowledge. It is not only about these cosmic sinkholes, it is about uniting the laws of the very large, gravity on a cosmic scale, with the laws of the very small, the quantum world of particles and uncertainty. A black hole, compact in size yet staggering in gravitational influence, forces those two realms to collide. It becomes a natural laboratory for extreme physics, and that is why it might hold the key to discoveries that reshape how we understand reality. Throughout history, whenever we have probed extreme conditions, whether at speeds brushing against light, at tiny atomic scales, or within immense gravitational fields, we have learned something fundamentally new. These objects may be telling us that our current theories are incomplete, and that something unexpectedly elegant is waiting beyond the edge of what we can currently describe. It is also worth noting how a black hole influences the grand scheme of the cosmos. They are often portrayed as purely destructive, and they certainly can be. Anything that wanders too close can be torn apart and swallowed, but they might also play a creative role in the universe. The largest examples, the supermassive ones at galaxy centers, act like cosmic engines. When material falls toward one of these giants, before it crosses the horizon, it often forms a spinning disk of superheated gas and dust, an accretion disk. That disk can heat up to millions of degrees and shine brilliantly in X-rays and other wavelengths. The same process can launch two gigantic jets of particles from the poles at near light speed, blasting into intergalactic space. Those jets and the energy released can influence star formation across a galaxy by heating and pushing around gas that would otherwise cool and collapse into new suns. It sounds counterintuitive, but by throttling or regulating star birth, these dark engines might actually help galaxies evolve in ways that allowed stable environments, and eventually life, to arise on planets like Earth. In our own Milky Way, the central black hole, Sagittarius A, is relatively quiet now, but in the past it may have been far more active, shaping the environment of our young galaxy. The presence of a supermassive one seems to be common in galaxies, and there is a correlation between the mass of that central object and certain properties of the galaxy's central bulge of stars. That hint suggests co-evolution. The galaxy and its central gravitational heavyweight grew up together, each influencing the other. So these entities can be both destroyers and creators in a cosmic sense, tearing apart stars on one hand, while also shaping the conditions for new stars and controlling the growth of galaxies on the other. Let's not forget stellar mass black holes too, the ones only a few times the mass of the Sun. When they form from supernova explosions, they can also trigger new star formation by blasting the surrounding space with energy and shockwaves. And when two of them merge, as detected by gravitational wave observatories, they unleash colossal bursts of gravitational energy, rippling space-time itself. These events tell us that these objects are dynamic players in the cosmic story, not just silent voids waiting for something to fall in. They are more like beating hearts in the galaxy, occasionally thumping with energy that can be felt across the universe. However, the drama truly comes alive when we imagine encountering one directly. Let's spin a hypothetical scenario that ties together what we have learned in the spirit of the black hole apocalypse. Imagine in some distant future, an unlucky star wanders too close to the central gravitational giant of its galaxy. This could be a star not unlike our Sun. As it gets closer to that dark behemoth, the side of the star facing it feels a much stronger pull than the far side. The star begins to stretch. Eventually, the tidal forces overwhelm the star's own self-gravity, and it is torn apart in a spectacular event called a tidal disruption. From afar, an astronomer would see a sudden flare of light as the star's gas is shredded and heated, with some of it forming a bright, swirling accretion disk. It is a last scream of light from the star as it is devoured. Over weeks and months, the monster consumes a chunk of that star's mass. This kind of event is not just theoretical. We have detected such flares in distant galaxies. It is like watching a cosmic predator feeding. Now imagine an even more fantastical scenario, a black hole on a collision course with our solar system. This is extraordinarily unlikely. Space is immense, and these objects do not typically wander in such a convenient, catastrophic way. But as a thought experiment, it shows how extreme gravity can get. If a small one, say a few times the Sun's mass, passed through our system, its gravity would wreak havoc on planetary orbits. It could sling planets out into interstellar space, or send them plunging into the Sun. If it passed very near Earth, tides would rip the crust, triggering apocalyptic earthquakes and volcanic upheaval. Ultimately, Earth could be torn apart and swallowed. That is a true doomsday scenario. Fortunately, nothing suggests any such object is coming near us, and the supermassive black hole in the centre of our Milky Way is about 26,000 light-years away, posing no threat to Earth. Still, thinking about this scenario underscores how powerful these entities are. It is a reminder that in the cosmic arena, there are forces that make our everyday experience of gravity feel like a gentle breeze, bringing our focus back to the enigma at hand. After journeying conceptually inward and surveying the landscape of modern physics ideas, where do we stand? We stand before a door marked "Do not enter," wondering what lies beyond it. What's inside a black hole might ultimately be a question about the limits of human knowledge. It forces us to contemplate infinity, the nature of space and time, and the unification of fundamental forces. It is almost a philosophical question as much as a physical one, because it touches the foundation of reality. From the perspective of Einstein's relativity, the interior ends at a singularity, where the known description of space and time breaks down. From the perspective of quantum theory, that answer feels unsatisfactory. Nature should find a way to avoid infinities and preserve information. So the interior could involve a new phase of matter, a new state of space-time, or an entirely different kind of structure that our current language can only gesture toward. It could be the birthplace of a deeper understanding of physics, where quantum mechanics and gravity become a single, coherent story. Until we have a complete theory and strong observational clues, we live with multiple pictures in our head, each compelling in its own way. A jittering ball of strings, a tiny rebounding core, a violent furnace of energy, or a realm where the usual meaning of space and time simply dissolves. Our imaginary astronaut Alice, unfortunately, never gets to report back. For her, the inside became the end of her personal story. But she also became part of the object she fell into. In a sense, that means her information is woven into whatever the true internal structure is. If one day it dies in a final flash, or leaks energy slowly over an unimaginable span of time, the atoms and information that once made up Alice might be released back into the cosmos in some form. It would not be Alice as we knew her, of course, more like her atoms recycled, her story written into the subtle pattern of radiation, like an almost poetic signature hidden in a Hawking photon. It is a strange kind of cosmic afterlife, to be smeared out across the universe as whispers of quantum information. In the end, the interior of a black hole remains one of the greatest enigmas in science. It is a place, if we can even call it a place, where our laws of physics as currently formulated simply surrender. To truly know what lies inside is to complete one of the biggest quests in physics, unifying the large and the small, resolving paradoxes, and perhaps discovering entirely new concepts of space, time, and matter. The answer could come from bold new theories and from subtle clues in high-tech observations. Every time we build a more powerful telescope or detector, we test these objects in new ways, watching their dance with stars, imaging their shadows, and catching their mergers through gravitational waves. Each observation is another piece of the puzzle. As we conclude this journey, it is worth reflecting on how remarkable it is that humans, tiny creatures on a small planet, can even ask these questions. Black holes were once thought to be mere mathematical curiosities. Even Einstein doubted they could exist in nature. Yet now we know they are out there, by the millions or billions, sculpting the cosmos. We have detected them, imaged them, and woven them into our understanding of how the universe behaves. They challenge us to think beyond the familiar. Peering into a black hole is like peering into the ultimate abyss of knowledge. It is both frightening and awe-inspiring. Frightening because it reminds us of our cosmic fragility and the limits of our power. Awe-inspiring because it shows there is so much more to discover, realms where reality is so extreme it defies imagination. So, what is inside a black hole? It could be the end of the line for matter, or the beginning of something new. It could be a monolithic pit of doom, or a strange cosmic seed carrying the information of everything it has consumed. It might be a place where space turns into time, and time turns into space, or where quantum ghosts of all that fell in linger on the boundary in a kind of encoded form. As of now, we cannot know for certain. But by exploring these ideas through thought experiments, physics, and astronomy, we edge ever closer to answers. One day, a breakthrough in theory, or a clever observation, might give us a firmer picture. Until then, these objects keep their secrets behind the veil of the event horizon. In a poetic sense, one might say that inside a black hole lies the human drive to understand the unknown. Each time we push against that frontier, We turn what once seemed like science fiction into science fact. The journey to uncover the truth of what lies beyond the horizon is far from over. It is one of the most exciting frontiers of science. And while a literal black hole apocalypse is not on our worry list, the term is a fitting metaphor. These entities represent an apocalypse of conventional understanding, forcing the death and rebirth of ideas in physics. They compel us to confront the ultimate extremes. In doing so, they light the way to deeper truths about the universe. As we close this exploration, imagine the camera of your mind pulling back from the scene of a black hole. You see the darkness, a sphere of nothingness in space outlined by brilliant stars behind it. It is ominous, yet majestic. You know that inside that darkness is something incredible. You are just not sure what. It could be crushing doom, or a hidden world of quantum phenomena. Whatever it is a testament to the richness of the cosmos. Black holes, in their silence, challenge us to listen harder to the whispers of the universe. They are not the end of curiosity, but a doorway to the next chapter of discovery. Until we can truly answer what is inside, we will keep asking, keep theorizing, and keep exploring, because that is what we do. The mystery pulls us in just as surely as gravity pulls in light, and perhaps one day, the secrets it holds will finally see the light of day, transforming our understanding of reality forever.